All right, everybody. So welcome to Unit 1 review for the school year 24-25. All right, we're actually going to skip number 1. Let's go to number 2 very quickly. All right, so number 2 says, base your answer to the following question on the data table below and on your knowledge of earth science. The table shows air temperatures recorded under identical conditions at 2-hour intervals on a sunny day. Data were recorded 1 meter above ground level, both inside and outside of a glass greenhouse, right? So we see the data table that's given here, right? And it says, let me just erase this out the way, apologize. So it says calculate the rate of change in the outside air temperature from 8 a.m. to 2 p.m. in Celsius degrees per hour. So when we're doing any sort of problem, it's good for us to just highlight key parts, especially when you're doing a calculate a rate of change, right? Because I see two categories of information over time: outside air temperature and inside air temperature. So the problem's going to tell me what I need to focus on. So it says calculate the rate of change in the outside air temperature. All right. So that means I'm only looking at the outside air temperature from 8 a.m. to 2 p.m. And my units is going to be in Celsius degree per hour. So what is my rate of change formula? So on my reference tables, I apologize very quickly. On my reference tables, here we go. And I'm going to look at page 1. The rate of change formula is right here. Rate of change equals change in value over time. So when I take a look, I'm going to rate of change is equal to change in value over time. All right. So what is my change in value? It was 8 a.m. to 2 p.m. So my value was originally at 15 degrees Celsius and it changed to 18 degrees Celsius. So what that means is my value is going to change. I'm going to do big minus small, bigger number by small number, right? Because it's the absolute value for earth science. They just want the change in value, not the direction. So I'm going to do 18 degrees Celsius minus 15 degrees Celsius, and that gives me 3. And my time period from 8 a.m. to 2 p.m., that's going to be 6 hours, right? 8 to 9 is 1 hour. 9 to 10 is 2. 10 to 11 is 3. 11 to 12 is 4. 12 to 1 is 5. 1 to 2 is 6. So from 8 a.m. to 2 p.m. is 6 hours. So I'm going to put 6 hours on the bottom. And that gives me 6 hours here. And when I do 3 degrees Celsius divided by 6 hours, I end up with a final answer of 0.5 degrees Celsius over hour. All right. Units are very important. And so that's why whatever units your change of value is, you're going to keep it on the numerator. Whatever time period, in this case, the problem even tells you what the units is going to be right here. All right, number 3. Number 3 says the diagram below represents the mass and volume of a mineral sample being measured. These measurements were used to determine the density of the mineral sample. It says, what is the mass of the mineral sample? So I'm looking for the mass, okay? Now, the mass of the mineral sample, remember, this is a triple beam balance, right? So when you place the mineral sample here, you're going to balance out these weights until this right here is balanced out or evenly leveled, right? And all you're going to do is add up all the numbers. So I see 60 here, 60 grams here, and I see 0 here, right? And I don't see any other numbers highlighted, right? So therefore, my mass is going to be 60 plus 0, and that's going to be 60 grams. Remember, when you're looking for the mass using a triple beam balance, you're going to add up all the numbers that the weights are highlighted in. Okay? For B, it says, what is the volume of the mineral sample? Let me change this in red now. All right? What is the volume of this mineral sample? So when I'm looking right here, all right, this was the volume of the liquid before the mineral was put inside, right? So when I look at it, how much is each line going up by? I see 20 and 5 lines until 30. So just by my eye test, it seems as though each line is going to be going up by 2. All right, it's going to be going up by 2, right? 10, 12, 14, 16, 18, and 20, 22, and that line 24 right here. All right. So therefore, when I zoom out, the volume of the liquid before it was 24 what? Milliliters. This was the volume of the liquid before the sample came in. Now, when I put the sample, what is the new volume? So when I remember, each line goes up by 2. So if this is 30, right? This is going to be 32. And this is going to be 34. So when I didn't put the sample in, it was 24 milliliters. When I put the sample in, it was 34 milliliters. How much volume, right, was added once the mineral sample came in? So how much did the volume change by? 30 milliliters minus 24 milliliters. And so therefore, the correct answer is going to be 10 milliliters as the volume. All right. That's how much space that it took up. Before it was 24 milliliters, I put the sample in, it risen to 34 milliliters. It increased by 10, and so that's my volume. All right, number 4. It says basic answers to the following question on the data table below and on your knowledge of earth science. The data table shows the date, location, barometric pressure, and wind speed at the center of Hurricane Irma at 12 noon from September 11th through September 7th through September 11th, 2017. The map shows the latitude and longitude coordinates in a portion of the Southeast United States and the Caribbean. And so the data table is given here. So it says describe the general relationship. So boom, it's a relationship question between the barometric pressure and wind speed for Hurricane Irma. So when I get a relationship question, I know I'm going to be comparing 2 characteristics, right? I'm going to be comparing barometric pressure and wind speed. So I want to know what is happening, right? When one category is increasing or decreasing, what's happening to the other category, all right? So when I'm going to zoom in, I'm just going to, let's compare, all right? So when I go from 21 to 27, it's been increasing. I'm just going to put a plus in between, okay? When I look here at wind speed, it goes from 157 to 130, it's decreasing. I'm going to put a minus. And I'm going to test out a couple of these numbers. When I go from 27 to 37, it's increasing. When I go for wind speed 130 to 113, it's getting smaller in between. I put a minus. Then when I go from 937 to 929, it's decreasing. I'm going to put a minus in between. And then when it goes from 113 to 118, it's increasing. I'll put a plus. Then when it goes from 929 to 970, it's increasing again. But I'm going to look on the other side. It goes from 118 to 161. It's decreasing. What am I noticing? Every time the barometric pressure number goes up, the wind speed goes down. When the barometric pressure right here goes down, the wind speed, what does it do? It goes up. It seems as though that whatever that the barometric pressure is doing, the wind speed is doing the opposite. When barometric pressure is increasing, the wind speed is decreasing. What kind of relationship is when one category is increasing and the other category is decreasing? That is an indirect relationship. All right. It's an indirect relationship. All right. If both categories are doing the same thing, right? If they're both decreasing together or increasing together, then it would be direct relationship. But since it's doing the complete opposite every single time, there's going to be an indirect relationship. I'm going to put the answers here to show you what you also could have said. So you could have also said here, morning. You could have also said here, as barometric pressure increases, the wind speed decreases. You could have said the higher the wind speed, the lower the pressure. You could have also said an inverse relationship or negative relationship. Either of those answers would be fine, even if you said indirect relationship as well. All right, number 5. Number 5 says, what is the approximate percentage of Earth's surface that is covered by the hydrosphere? So remember, hydrosphere, what does a hydrosphere mean again? Hydrosphere represents all of the water on Earth's surface. All right. And so this is just something, sorry, this says surface. I know my handwriting is a little bit horrible, but this says Earth's surface. So what do we know? What did we learn in class? We know that the Earth, a large part of the Earth is covered in water, right? Almost 3/4. And so therefore, the percentage of the Earth that's covered by the hydrosphere, right, is going to be 70%. All right? So that's something to keep in mind. Number 6. Number 6 says the subtropical jet streams are fast-flowing air currents located in the atmosphere about 10 kilometers above the surface of the Earth. Let me just pause right there. All right, these jet streams are located in the atmosphere about 10 kilometers above the surface of the Earth. In which layer of the atmosphere are the subtropical streams located? Well, they told us the subtropical jet streams are located 10 kilometers above the surface of the Earth. What page of the reference table shows me the different layers of the atmosphere? Page 14. All right. So I know that the jet streams are located at 10 kilometers. So I'm looking on my kilometer side, right? That's why it's important for us to read the question. And that means I'm going to look here and I'm going to find 10. Well, right here, I see each line is going up by 10, right? 10, 20, 30, 40. So therefore, at 10 kilometers, we are still in what layer, everybody? We are still in the troposphere. All right, there are 4 layers of the atmosphere: the troposphere, the stratosphere, the mesosphere, and the thermosphere. At 10 kilometers, we are still in the troposphere. Number 7, which is the most abundant element in the Earth's crust? All right. Well, there is a page on the reference tables, right, that mentions the elements in the Earth's crust. What page, everybody? We're going to scroll to page 1. So let's scroll to page 1. And we're going to scroll all the way. So make sure I have your reference tables out. And we're going to scroll right here at page 1. And look, it says the average chemical composition of the Earth's crust, right? So I see elements here, I see crust here. So So the question states, let's take a look real quick. What is the most abundant, right? That means the most abundant element in the Earth's crust. So when I look at the Earth's crust, whether I go by percent by mass or I go by percent by volume, the element that is the most abundant, right? That means the most of, is going to be oxygen. So my correct answer is going to be oxygen. All right, number 8, it says, base your answers to follow questions of the passage and photographs below and on your knowledge of earth science. The photographs show 2 celestial objects before, during, and after a solar eclipse that was observed in Kingston, Tennessee at 2:37 p.m. on August 21st, 2017, taken from a fixed position. All right. So during this time, you would have already read, okay, the passage about solar eclipse and the Saros cycle. So the question says, predict the next year after 2017. Next year after predict, so I'm going to predict the next year after 2017, when the total solar eclipse path associated with this Saros cycle will return to the same section on Earth. Okay? So here's some of the things to keep in mind. Okay? It says will return to the same section on Earth. So in the reading, it tells me a Saros cycle lasts 18 years. Okay? But it says since 8 hours is approximately 1/3 of Earth's daily rotation, it takes 3 Saros cycles for a solar eclipse to return to the same section of Earth. Look what the question I see. It literally says right here, Saros cycle will return to the same section on Earth. Look, solar eclipse to return to the same section on Earth. So as you can see, right, they tell us the time period that it takes. It takes 54 years and 34 days. So what does that mean? After 2017, the next time that the total solar eclipse path with this Saros cycle will take place, it will take place when? The next 54 years. So 2017 plus 54 years later, what does that give me? Adding up. And so my next time that this will occur will be 2071. All right, number 9. So number 9 says basic answers to the following question on the passage and the data table below and on your knowledge of earth science. The data table shows a percentage of quarries in New York State that is mine-specific type of bedrock to produce crushed stone. A quarry is an area where rock material is removed. So you're going to take time to read this. If you need to pause the video, go ahead and pause, but make sure that you're reading, annotating, all right? So it says, explain why shale is rarely used in the building and construction industry. So when I look at this question, when I get a question, a reading question, I'm going to read and see what information that I can pull from the passage that's going to explain why is shale rarely used in building and construction industry. So after you've been reading, all right, it talks about shale right here. Shale, a common rock found in New York State, is rarely mined. It says right here. Look, why is it rarely used? It is rarely mined because why? It tends to weather too easily to be used as a construction material. You see how they gave you the answer right here. All right. So why is it that shale is rarely used in the building and construction industry? It's because it tends to weather too easily. And the word weather just means to break down. All right. So for number 9, if you wrote, I'll put the answer right here. Shale weathers too easily. All right. You would be correct. All right. Number 10. Number 10 says basic answers to the following question on the graph below. The graph shows the recorded change in water level, ocean tides, at a coastal city in the northeastern United States during day 1, right? So it's giving us the height of the water, and it gives us the height of the water during 1 day, right? What inference about tides is best made from this graph? All right. So what inference? So all this information is telling me is about the height of water throughout 1 day. So when I'm looking, one of the things that's going to help me is to remove false choices. All right, I'm going to move false choices because an inference can just also be a conclusion. So let me see. It says the hourly rate of tidal change is always the same. So they're saying that the tide changes the same every hour. That is not completely true. So I'm going to remove that. It says the rate of tidal change is greatest at high tide. The rate, seeing how fast it is. Not necessarily. We can't really pull that information off. All right. Not necessarily. Okay. Tidal change is a random event, right? A random event means that we can't see a pattern, but we do see a pattern. It's going up, it's going down, it's going up, it's going down. So therefore, the correct answer is the tidal change is cyclic, all right? When you see a pattern that is repeating itself, okay? The fact that it goes at a peak, even look at the time periods for the peak. The peak occurs between 12 and 2, right? The peak occurs between 12 and 2. When I to look between 12 and 2, it looks like the peak occurs again. So there's a similar pattern that takes place. When we're seeing a pattern, all right, for an environmental change, that means that it has a cyclic relationship. Number 11, the graph below shows a total number of deaths per month caused by lightning in the United States between 1959 and 1990. So when I look at the chart, number of deaths caused by lightning, and these are the months. It says, based on the information on the graph, which prediction about lightning deaths in the United States in the year 2000 would be most accurate? Okay, based on the graph given. A, it says most deaths will occur along the eastern coastline. On the deaths, does it even tell us where in the United States? We don't know enough information, right? All I know is that most deaths happen in July. That's all I know about what most deaths is. So it can't be that. The number of deaths will exceed 900. Okay. But in the year 2000. That is possible. The number of deaths may actually, no, we can't even make that prediction because look, the chart doesn't even go past 900. So we can't even make that prediction. All right. And then if we look at C, the greatest number of deaths will occur during the summer. Let me check if that's true. My summer months is June, July, and August. And when I look, my bar graphs are the highest during these months. That looks like a true statement. So I'm going to put a check on that and let me see. D, most deaths will be the results of hurricanes. Once again, this graph is talking about lightning. It says nothing about hurricanes, so we can't even use this information. So the correct answer is going to be C. All right. When you have questions like these, you're basically looking for, okay, which statement is true? Which statement would be the most accurate? Which statement can I draw the best conclusion from in these graphs? Number 12, which graph shows the most probable effect of environmental pollution on the chances of human survival? Well, I see pollution is on the x-axis, right? And what do we know about the x-axis? The x-axis, whatever variables on the x-axis means that it is increasing. All right, let me zoom in here. If there's a variable on the x-axis, that means that it is increasing. So right now, all of these graphs are telling me that pollution is increasing. Right? Pollution is increasing. So the question becomes, which graph tells me what happens to human survival as pollution increase? Well, what can we say? Isn't human survival going to be less if there's more pollution? Which graph tells me that the chances of human survival will decrease as there's more pollution? Which chances of human survival is on the y-axis. So that means my line should be heading downwards as pollution increases. And that's why the correct answer is B, right? As more pollution increases, your line should be heading down, which represents chances of human survival. Number 13, it says the graph below shows the relative amount of air pollution over a city for a period of several years. All right. Which statement about air pollution over the city is best supported by the graph? Let's look at A. It is decreasing at a constant rate. This is false because if it was decreasing, that means that I would see a line that would continue heading downwards through the entire time, like that. But we see sometimes that the line goes up. So that means that this statement is false. All right. It is increasing at a constant rate. Well, when I take a look, increasing at a constant rate the entire time means that I would have a line that would be creeping upwards. And that's not the case, right? You see the line is going up and then it's going down. It's going up and then it's going down. It's going up and then it's going down. It's going up and then it's going down. So it's increasing and decreasing, okay? Now C, it has a cyclic event. I gotta ask myself, a cyclic event means that I see peaks, right? I see a repeated pattern. Well, let's see what pattern do I see. I see that in the middle of the year, I see a peak in the middle of the year. It gets to its highest point. I see another peak in the middle of these 2 years. I see another peak in the middle of these 2 years. I see another peak in the middle of these 2 years. This represents a cyclic relationship. And the fact that I see this pattern increasing, that definitely means it does not, it does have a pattern, which will make it false. That's why the correct answer is choice C. All right, number one, it says basic answers to the following question on the table below, which shows a concentration of ozone in ozone units in Earth's atmosphere at different altitudes. One ozone unit is equal to 10 to the 12 molecules per cubic meters. Okay. And it says on the grid provided, construct a line graph of the ozone concentration in the atmosphere recorded at the different altitudes shown on the table by plotting the data from the table and connecting the points. Plotting the table from the table and connecting the points. Now, I'm not going to plot each one. All right, I will show you the answer at the end. But here's something that is very important. We need to know how much each line is going up on the x-axis, and we need to know how much the line is going up in the y-axis. All right. So like I said in class, if you ever want to know, it's going to be constant, right? It's going to be the same repeated pattern that's going up by. So if you ever want to know how much each line is going up by, find two numbers, all right? So let's say I find 50 and 60. You know what? Let's even go better. Let's find 0 and 10, all right? So I find 0 and 10. And I'm going to ask myself, so I'm going to put from 0 to 10. Whoops, here we go. Sorry, here we go. From 0 to 10. I'm going to write 10 on my numerator because they're 10 apart from each other. All right, 10 apart. I'm going to ask myself, when I start at 0, how many lines do I need to go up by to get to 10? 1, 2. So I need to go 2. They're 10 apart, divide by 2, and that lets me know each line is going up by 5. So on the y-axis, each line is going up by 5. The same thing works here. I'm going to find two numbers given. You can start from 0, 0 to 1. All right, so I'm going to put 1 on the numerator side. All right, my 1 should be better. And I'm going to find out how much each line, how many times do I have to go up starting from 0 to head to 1? 1, 2, 3, 4, 5. I had to move 5 times to the right. So I'm going to do, they're 1 apart, divide by 5. And 1 divided by 5 gives me 0.2 as my answer. All right. So that means on the x-axis, each line goes up by 0.2. And on the y-axis, each line goes up by 5. Right? So let me just erase everything here because this is what we solved for. All right. And I'm not going to do for all, but I would definitely tell people, hey, this is what you should do to fill in the gaps, right? So I know each line goes by 5, so I'm just going to mark it 0, 5, 10, 15, 20, right? 25, 30, 35, 40, and so on. You can continue on, okay? And even for the x-axis, I'm just going to do for some, all right? Each line is going up by 0.2. So I'm going to do 0.2, right? 0.4, 0.6, 0.8. Why am I doing that? All right. It's just that way when it's time for me to plot my points, right? Let's look at my first point. I see an altitude of 0 and 0.7. So now my altitude is going to be 0 right here and 0.7. 0.7 is going to be in between 0.6 and 0.8. So it'll be right here. All right. And filling in those gaps is not something that you have to do. You don't have to, but it just helps you to know when you're stuck on a point and you're not sure where I would plot a point. It just helps. It helps you to double check your answer. So especially if you have time, I would even say try to fill in those spots One thing I would also say too, if you see that the lines are narrow like this, you could just write your number vertically, 0.2, right? Or you can turn the paper, right? 0.4, right? Or 0.6. And once you get the pattern and so forth, you'll be fine. That is the end of this video. All right. Once again, this video is talking about Unit 1 Review 24-25. If you have any questions, let me know. Make sure to like, share, and subscribe. All right, everybody, have a blessed day.